explain why this works. So let's think about the corollary we have here. Or maybe before we begin, let's review briefly what was Lagrange multiplier. So it's based on this theorem, and this theorem tells you that if a point on a constraint, which is the level curve or level set of given multivariable function, is an extremal point of some function, which is called the target function, then the gradient of f and the gradient of g, where f is the target function and g is the function that defines the constraints, are parallel. So basically we have this equation right here. This one. So this theorem tells you that if the point is extreme, then the two gradient vectors are parallel. But when you apply the Lagrange multiplier, we have to find the point where the gradient vectors are parallel, and then knowing that these points whose gradient vectors are parallel could be the candidate of the extremal point, and we have to actually check whether these points are extremal or not. Sometimes we not get an extremal point. So okay, so here's a corollary. Okay, so let me erase this and prove the corollary here. It says that the gradient vector is the direction where the value of function increases the most from the point x0 and y0. So think about the situation that we have. We want to move from the point x0 and y0. So when you move your point x0 and y0 on two-dimensional plane, there are 360-degree direction. Well, actually there are infinite direction, but you have all direction that you can move. You want to find a unit vector. Suppose that we have a unit vector. I just want to move by a unit, but the question is, in which direction should I move to increase the function f the most? So let's say this u vector ab is a unit vector, and I want to maximize the increase of the function to the direction of u. So I want to maximize the directional derivative of x0 and y0. Okay, so now, although the function f is a function of x and y, our objective is to find a and b which maximize this directional derivative. So this ab becomes the variable that we have to find, and this becomes the constraints, and this becomes the target function. So constraints consist of a and b. The target function, what is this? This is nothing but the gradient of inner product with u. So this is also a function of a and b. Basically this is a fx x0 y0 plus b fy x0 y0, the linear function. So how do we use the Lagrange multiplier? So we set this GAB to be a square plus b square, and we used f. So let's say we have large f to be the target function, a fx x0 y0 b fy x0 y0. So try to look for the point where these two gradient vectors are parallel. Then we have on the left hand side fx and fy. So we have a fixed point x0 and y0. So these partial derivatives are constant. Okay, so I just omit xy for convenience. And on the right hand side we have 2a 2b times lambda. So I want this to be equal. So basically I need a to be f over 2 lambda and b to be fx over 2 lambda, b to be fy over 2 lambda. Okay, but I want this ab to satisfy these constraints. So basically this is fx squared plus fy squared equals 4 lambda squared. So I fixed this my lambda. So basically lambda works as if it's a normalization of the vector u. Anyway, what I have as my vector u is that if I plug in this this lambda value, is that fx fy divided by square root of x squared fy squared. So simply I get a normal vector, the unit vector, in the direction of the gradient of f at the point x0 and y0. Okay, that's the point where I get the maximum of f. By the way, when I find the lambda in the process, I could get the negative lambda. Okay, because I have a square on the lambda side, so I might have a plus minus sign here. But how do I check whether which one is the maximize the directional derivative and which one minimize the directional derivatives? Simply put the value u, this vector u, into the directional derivative formula. If you have a positive a and b, you get the positive value. If you have negative a and b, you get the negative value, because this value becomes fx squared plus fy squared. Depending on the sign here, you get the positive value and negative value. Positive value means the function increases, negative value means the function decreases. So if you want to increase the most function, then you need to take the vector u to be the normal vector to, the unit vector to the direction of the gradient. If you want to decrease the most function, then you have to take the negative direction of the gradient vector. So this is very useful. Maybe this is the most useful application of Lagrange multiplier, because sometimes this is called the gradient descent, and that's used in the deep learning. That's the essence mechanism of the deep learning here. Maybe if I have time I will explain it later, but alright, so I'm relieved. Alright, so let's look at another version of Lagrange multiplier. So once you know the Lagrange multiplier on 3 variable function, you can increase that number of variables to arbitrary number, but in practice, this 3 variable function version is the most useful. So so let me read out the theorem first. So we have two functions, g and f, and if the point x0, y0, z0 is local extremal of the function f, this is the target function, restricted on the level set of g, so this is the constraints, so it means g equals to c. So this is the 3 variable function. The level set of 3 variable function is surface, not a line. Okay, surface on the 3-dimensional space. So you're looking at a value of function f on the points on this surface. There's a typo. If the gradient of g at this point is not 0, then there exists lambda such that two gradient vectors are parallel by the factor of lambda. So basically the same. So when you apply the Lagrange multiplier, you first start from this equation, try to find a point where two gradients are parallel, and then check if that point is actually an extremal. So try to find the minimum and maximum value of function f, which is given by x cube, y cube is z cube, not square, on the sphere of the radius 1 on the first octant. So by the symmetry, there are other 7 octant, but we only want to look at the first octant, which means that x and y, z are all bigger than 0. So I want to give a picture here. I want to show you a picture. So I'm trying to draw a sphere and the level set of the function f. So f implicit of x, y, z, x cube, y cube, z cube minus, let's say 1, and hold off, and I want my view, let's say also just take this axis and view. Okay. I put implicit 3. So that's the picture. Maybe I will give you a full picture here. And then let's say we have 2 here. So this is the picture of 2 surfaces. One is the sphere and the other is the surface of the level set of the function f on the level 2. So in you cannot graph the 3 variable function. You need 4 axes to draw that, or you have to draw with a color. But I just want to draw as a surface. The only way you can do is to try to graph the level set. So these how do I express this? So this surface, not a sphere, the surface, like these ones have all the same value of the function f, which equals to 2. So at every point on this surface, you plug in that to the function f, the value of function is 2. Okay, and you see there's no touching between this surface and the sphere. Okay, so there are no common point x, y, z, which satisfies that the g, which is x squared plus y squared plus z squared, is equals to 1, and f is equals to 2. So it means that no points on this sphere have the value f equals to 2. Okay, but if I decrease my level here, so let's say I have take 1 here. Here we have an intersection that's actually a tangent. So there's a point which 2 surfaces are touching each other. There are actually 3. So at these 3 touching points, these are common points of these 2 surfaces, which means that at these 3 points, the value of function f is equals to 1, and value of function g is also equals to 1. Okay, so let me take that other way. So I don't want to change the constraints. Our constraints is the sphere. Look at the slide. So I only want to analyze the point on the sphere. So what I want to analyze is the value of function f, which gives the level surface here. So until I decrease my level 1, there was no touching of these 2 surfaces, which means that any of the points on the sphere cannot attain the value of function at that level. But if I decrease the level to 1, then now it has 3 points, which just becomes the common point. So these 3 points will have the largest value of the function f, because other points, no other points can have a bigger value of function f, because there's no touching. Okay. So from now on, I will make an animation which I increase my c. So I'm going backward here from 0 to let's say 0 to 1, because after 1 there's no touching anymore, and how these two surfaces are intersect each other. So let's look at the picture. So I'm just using a first octant. So when c is 0, there are lots of touching. So there are actually points of curves that's touching each other. There are many points which attains this value c at the function f. So now I paused here. So this point in the middle, the red point, is now emerging from the middle and becomes a touching point. Okay, and I keep increasing my c. I keep going. There are lots of touching, and until I have lots of intersection, not touching, until I have touching point, 3 touching point here. Okay, so I also marked as red here, and then I keep increasing my c. So when I increase my c, there are still touching, there are still intersections, but until I get c, there are no touching. But then when I get c, there are all 3 touching points, as I showed before. And if I keep increasing my c, there's no touching, so no point can get a function value bigger than c. So now let's analyze what happens here. I want a point on the sphere which has extremal value of the function, whose level set looks like some curved surface on 3-dimensional space. Now I know that these 3 points, the last 3 point, is the maximum point. What would be the minimum? The minimum could be what could be the local minimum? Sorry, not minimum, not global minimum. So if you're looking at this picture, the beginning picture, this has no local minimum, right? This is not a local minimum. So if I keep increasing c, there are points nearby which has value f less than or bigger than this point. But when I get this point in the middle here, in the neighborhood of this point, all the value of function f is greater than the value of value at this point, because at this point in the neighborhood points are intersection of the sphere with the level set at the greater level c. Okay, so I know that this middle point is I didn't get the actual coordinate, I didn't calculate it yet, but in the programming I already done that. So in the middle point there is minimum point. I know that this is local minimum. Okay, but we passed that through. But in the middle we had 3 points also touching each other, but that's not local minimum nor local maximum. Let's see, what was the c here? So 1 over square root of 2. Let me draw that here. Oh, it's large. Okay, so this is our picture. We have 3 touching points. These are not local maximum, local minimum. What happens to the point. So here's the sphere point. So let's look at this one point here. If I move to this direction, this point, let's look at this point. It has already passed the touching, already passed the intersection with this level surface. So at this point on the sphere, the value of function is smaller than this touching point here. Okay. How can I delete this? Okay. Yeah. Right. So how about if I pick a point above this point? Let's say I pick this point. This is the sphere surface. Okay. So I did not. This point is still yet intersect between this surface and the sphere. Okay, so I need a larger level to intersect these two surfaces at this point above this point, at the touching point. So the value of function f at this point is larger than the value of the function f at this touching point. Okay, so on your left, the value of function is smaller. On above, it's larger. So depending on direction, there are points whose value of function f is smaller or larger. Okay, so this is not local minimum. It's actually a saddle, because it is extremal in the sense that it's tangential to each other. However, this is not a local minimum or local maximum. Okay, so by looking at the graph, you know that there are one local minimum, which rises on the middle point. Actually, the coordinate is coordinate was 1 over square root of 3, 1 over square root of 3, 1 over square root of 3. And there are 3 local, actually that's a global maximum too, but local maximum at these 3 points, 0, 0, 1, 1, 0, 0, and 0, 1, 0. Okay. So let's try to solve by hand here. So I want, let's say this is my g, x, y, z, and maybe I need more space. So gradient f is 3x squared, 3y squared, 3z squared, and that should be equals to lambda gradient of g, which is lambda times 2x, 2y, 2z. Okay, so I know that we have 3 equations: 3x squared, 2 lambda x, and 3y squared equals to 2 lambda y, and 3z squared, which is 2 lambda z. So don't erase x, y, z, although there are 2 x's and y's and z's on both sides, because these could be 0. So we're looking at this, x could be 0 or given by 2 lambda over 3, and y also 0 or 2 lambda over 3, and z also 0 or 2 lambda over 3. Okay, so depending on the choices, there are independent choices. You have a combination of point could be 0, 0, 0, or with 0, 0, 2 lambda over 3, or you could have 1, 0, 2 lambda, 3, and you could have all non-zero values, 2 lambda over 3, 2 lambda over 3. However, this cannot be the extremal point, but because this cannot satisfy these constraints. x squared, y squared, z squared equals 1. Okay, you have to analyze these 3 points. But if you've done that, assuming that you've done that, knowing that the picture, this is the local minimum, and what's the global minimum, like global maximum? Global maximum appears here, and in the middle, when you have only 1, 0, this is saddle point. So how do you check whether this is saddle or not? There are no systematic way. Okay, there's no systematic way to check whether this is a saddle or local minimum or local maximum. Only way and best way is to look at the neighbor points and see how the value of function f changes if you move your point a little bit to every direction. So if you try to do this by your hand, that will be very that could be wrong. That's very very naive way to do that, but also very dangerous way to do that. So try to use the MATLAB or other graphing device to try to find out the local maximality or minimality of the point. But if you have a better enumerating device or program, then you can check by simply looking at all the values nearby this point of the function. So anyway, it's the best we can do is find the candidate of the local maximal, local extremal points. The checking is the different issue. All right. Okay, so we have done that, and right. Let's look at this problem. Similar ones. Find the point of the graph which is closest to the origin. So I want to minimize the distance x squared, y squared, z squared. Although the distance is square of this, but minimizing the sum of square is same as minimizing the square root of this value. Okay, if you take the square root of this sum of squares as the target function, then your gradient is become very complicated, right? So I just need this. I will use this. So this is our g. This is g, x, y, z. So gradient g is y, z cube, 2xy, z cube, and 3xy squared, z squared. And lambda gradient g equals to gradient f, which is 2x, 2y, 2z. Okay, so we have 3 equations to solve for x, y, z, and lambda. Okay, you will only get 1 point which satisfies these equations. You can do it by your hand, which is simple analysis. I will show you how it looks like here. So let me draw f implicit picture x, y, z, x, y, z minus 2. So this method f implicit 3 graphs the implicit plot of the function. So internally assumes that this function it graphs the function value equals to 0. So when I want this to be 0, then I have to move this 2 to the left hand side so that this should be all 0. Okay, and then I also want to, well, let's graph this one. Did I make a mistake here? X, y, z. That's true. Okay, so I have a 0, 0, 0 on somewhere here. So axis 0, how far it should go? Maybe 2, 2, 0, 2, 0, 2. Okay. So this is the picture from 0, 0, 0 here, and I want the nearest point from this the origin, this origin. Let me try again. This origin to the surface here. So by looking, we don't know by looking at this graph. So I actually have to find the solution. Okay. So as you see in this picture, maybe I should put another constraints, because yeah, in theory you have to check the minimum distance between the origin and these 4 surfaces, but it's complicated. It just doesn't really necessary. So let me change this condition here on graph on the first octant, which means that x, y, z are all positive numbers. Okay, so put this condition on and try to find the positive x, y, z satisfies this equation. Okay, there are only one. And how do you know that that's the local minimum? There could be local maximum, or it could be the saddle point. After you find a solution, find a point which satisfies this equation, you have to draw, or you have to know at least a idea how the graph looks like to conclude that why this is local minimum or local maximum, local or saddle point. Okay. Right. And that's that. And what I want to show you is a different one. So let me show you another application. So it's not really an application that I wanted to make this to be a project for this semester if we didn't have this epidemic, but we don't have a project, so I will just show you what I made as a sample. So we have one. I'm searching for my code. So here we have where did I put that? Wait. Oh. Oh, here. Okay. Oh. Right. It's that one. Okay. Not sure whether this works. Okay, well, it works. Can you see the red lines here? Red dots? And what does it look like? Let me show you again. Maybe I will increase that one at 40. Can you guess what I'm trying to do by this simulation? What does it look like? Can anyone guess? Right. Yeah. So I was trying to simulate the raindrops. So this is some kind of surface, and suppose that you're raining. You're putting this kind of surface outside on a rainy day. I want to try to simulate how the raindrops follows from the sky and then along the surface. So there are point where it's local minimum here, and when rain drops, it will concentrate on this lowest level here. If it drops on somewhere in here, it will fall down outside. So that was my project actually, to sign you, but we don't have a project, so I'm just giving you how I did this. So basic idea is using the gradient descent, that always the water drop is affected by the gravity, and gravity wants to work on the direction where it decreases the potential energy the fastest. I'm not sure whether that's true in general, but anyway. So if you want to decrease the height, which means that you decrease the potential energy, then you should always move the gradient direction, right? So it doesn't matter when you're just falling from the sky, but when it touches the surface at one point, then from then you follow the water follows along the graph, the surface of the graph. So basically, I'm solving here. So let me change it to here. So basically, I want to solve this kind of equation. So let's say we have ct as xt and yt here. I want c prime t equals to minus of gradient of xt and yt. Okay. I want my trajectory always move in the direction of the gradient of f. Okay. So the problem is, in the previous example in the slide, we didn't care about the actual trajectory, actual parameterization. I just want the trajectory. Here I could done the similar way, but I want really to simulate how fast the water drop move along the surface. So I actually need to solve for t. I actually need to find a solution to this differential equation. But if a function is complicated, then it's not an easy task, so I used numerical solution by the MATLAB. So here's the code. Alright, well, anyway, so this is the setup, and where did I solve this? Yes, here. So actually this is inside a function. So I was given by a graph, the function which graph this surface, and the number of points and number of the starting points, starting heights, when the water drop starts, and each water drop has a random velocity, okay, because it depends. And the water drop is very light, but I was assuming that the velocity of dropping is different, so I gave a little bit of randomness here. And for every drop, I solved my differential equation having this as my x prime and y prime. Okay, do you remember how to solve the differential equation numerically using MATLAB? So first you have to find, in the system of differential equation, you have to set your differential equation on the left, which is x prime and y prime, and on the right, which becomes the function of x and y. Okay, so this first part is x prime and second part is y prime, and I used ODE 45 to find the actual solution. So it gives coordinates of trajectory according to the time. So that was returned as a combined way into C, and then what I did is just plotting this C every time. So every time if I try to compute the velocity and the trajectory, it could be a very well, that's not very efficient. So I just calculated all the trajectories of all water drops, and just that was the result. Let me change my graph a little bit here. So this is my picture. So the good thing about this code is it works for any type of function. Yeah, you can type any functions, any formula here to work with. So for example, I can even put sine y squared. I think maybe I'm not sure whether that works. Let me see. Y squared, maybe a little bit of sine here. Well, that can be a little bit. Okay, I gave a little bit of wiggle here, and you see that if it moves small, if it moves slow, then the line, the length of the line is short. If it moves fast, the length of the line is long. It's not intended, but it's actually what MATLAB does. Anyway, I'm not going to share this code. Maybe I will use in the next lecture, maybe next year. So I just showing you could do this using MATLAB on the base of this Lagrange multiplier. And I think it's very important. For example, if you have a movie industry, they have all the engineers to make us this CG makes real, right? And like animation, and also many blockbuster movie uses engineers to make a movie out of nothing but simulation, computer simulations. And who knows, you could work in that industry later, and you could use your knowledge on the Lagrange multiplier and gradient descent to create a new one. And okay, so that's it. I think that's it for our previous week, and we have a holiday on It's Friday, so we're not going to give a new material. We solve. Oh, maybe okay. So I forgot this problem. Sorry. So this is an important one. So let me try to do this. Okay. All right. Look at this one. So we have looks like a target function f, and our domain is not a level set, but it's a disk. Okay. So this kind of problem mixes the Hessian, the method of Hess's method, and the Lagrange multiplier. In Hess's method, it tries to find the local extremal on the domain, entire domain of function, okay, on the plane in this case. On Lagrange multiplier, by the way, it only finds a local extremal on the restricted set, which is the level set of some certain function. So I have to divide my disk into two parts. One is the entire region, which is, let's say, interior of D, which is x squared y squared less than 1. And I have to assume that this is subset of R2. And another area, which is the boundary of the disk, which is x squared plus y squared equals to 1. So on the boundary, I can use a Lagrange multiplier. On the disk, inside of the disk, I need to use the Hessian, assuming that this disk is a subset of R2, and search for local extremal on the R2 and just pick out the points inside of the disk. Alright, so using the Hessian, we have this function. So we have fx equals to 2x plus y, fy equals to y plus 2 x plus 2y. I want this to be all 0. Try to find the critical point. So what's the point? We have, oh, that's only 0, right? That's the only point, right? There are no other local critical point, right? So let's try to find out whether this is local minimum, maximum. So we have 2, 1, and fyx 1, 2. So we have determinant equals to 4 minus 1, which is 3, which is positive, and this is also positive. It means that this point is local minimum. Okay, so we have a local minimum inside of the disk, and that's only minimum local extremal on the entire domain. Now, that's not entire local minimum inside of the disk. So we have a boundary of the disk. There could be a local maximum on the boundary of a disk, although there's no local maximum on the entire domain. Because of the boundary, you could have one. So let's use the Lagrange multiplier. We have gxy set as x squared plus y squared, and gxy lambda is equals to gradient f, which is 2x plus y, x plus 2y. So we have 2x plus y equals to 2 lambda x, and x plus 2y equals to 2 lambda y. So it seems like you have two equations to solve for 3 variables, but you have one more equation, which is x squared y squared equals to 1. Okay, you have 3 equations. So first, try to solve for first 2 equations and try to rewrite as x and y in terms of lambda, and then plug into the constraint and find out what lambda is. You can do that yourself. And if you have found the local extremal, then you have to check whether this is local minimum or local maximum. So you have to draw it anyway. So let's draw the function. So here we have graph of functions. Minus length space minus 1 to 1, and let's define my function xy square plus xy and y square, and surf xy and fxy. That's my picture here. Okay. All right, let's see what happens on the boundary. So I know that at 0, 0, 0, 0 here, there is a local minimum. Actually, that's a global minimum though. And let's see, I want to parameterize my circle boundary by zeta. So in space minus 0 to pi, and plot 3 of cosine zeta, sine zeta, and cosine zeta, and sine zeta. Make it red with thick line 2. Right, that's my circle. So if you're looking at the projection line, it's a circle, right? So looking at the circle boundary here, the value of function is depicted as a z-axis. So this has the, here we have 2 local maximum on the boundary. Actually, that's a global maximum too. And here we have a local minimum, but it's not a global minimum. Global minimum is at 0, 0. But it's a local minimum. So 2 global minimum, global maximum, and 2 local minimum, and 1 local global minimum. Okay, that's all we have for extremal points. So I draw that in this rectangular, the square region. You can also draw this on the sphere, the disk region. So it depends on the mesh grid here. So we have r zeta, sorry, let me make it capital, r zeta as mesh grid in space maybe from 0 to 1 to 20, in space from 0 to 2 pi, So the difference between this first one and second one is that the first one I have 2 line spaces, and the second we have 1. When I have 2 line spaces, the first one is the subdivision of r, the first variable, and the second one is subdivision of the second variable here. So after that, I take a mesh grid of these 2 subdivisions. So this r and theta becomes n by n matrices. But anyway, instead of I'm using x and y, I take x to be r times cosine theta, and y to be r times sine theta. Then I get rid of all the others. So although this picture cannot be drawn in the circular region, but just the graph is circular now. Okay, it's a better picture, right? Okay. So I think that's everything. That's everything for we have to know before we go into the integral part. So the next week, we're going to solve more problems. Could be a little bit of challenging problem. And yeah, that's all I have to say. We have plenty of time, but we can finish early. Is there any questions? Okay, on Friday it's a holiday, we don't have a class. Okay, so let's finish our lecture here and let me announce something.